more precisely what we'll be doing is we have some bounds on an operator, right? We have some operator between, in this case, LP spaces, and we'll be trying to get. We have some set of bounds, and we have some other set of bounds, and we're wondering if we can get intermediary bounds for the operator. And this is pretty common and sort of a great technique, and a useful technique. So let's. We're heading towards. Today we're going to talk about the Riesz Interpolation Theorem, and let me start off by giving the motivation. So here it is. The motivation is the so-called Hausdorff-Young inequality. Okay, so so given a function in L2, suppose we have some function on L2 on the interval 0 to pi. So and then you define Fourier coefficients. Fourier coefficients of f we define as a sub n is defined to be the integral of f against e to the minus I in theta theta. And you have some normalizing, you throw in some normalizing factor. So the integral of 1 is 1. So you have these things, these are called the Fourier coefficients. How many of you have seen Fourier coefficients before? Most of you. How many of you have anyone not seen them? Spencer? Okay, that's all right. Don't worry. So we have a function, and then we create these things called the Fourier coefficients. Okay. You integrate this function against the against e to the minus I theta. Okay. And so then you create this thing we call summation a sub n e to the I in theta, and then we make this over z. The Fourier series. Fourier series associated with f. Okay. So it's basically you are. What this is telling you is basically how much of e to the I in theta is in your f theta. Okay, it's taking. This is basically taking an inner product of f. You can think of this as an inner product of f against e to the I in theta. Okay, the e to the I in thetas form an orthonormal set. And you're figuring out what the coefficients are by taking the dot product, taking the inner products of f against that orthonormal set. And then you say, okay, well then, to reconstruct my function, I'm going to need, a sub n of e to the I in theta, and I sum all those guys together, and hopefully I get back, we call this, hopefully I get back f. So we call this the Fourier series associated with f, and we write that f twiddle a n e to the I in theta. Just to say that this guy is associated with this Fourier series. Okay. And the big question is, does this really recover your function? Do you really get back your function, and in what sense do you get back your function? Do you get back your function in a pointwise sense? If your function is, what kind of smoothness do you need on your function to recover your function so that this actually recovers your function in a pointwise sense, etc. So, okay. Okay. So let's see. Let's write. Let's notate. Let's notate as follows. We'll notate the L2 norm on this interval as the normalized we throw in, we'll throw in the factor in this case, just for convenience. And we'll notate this is just the standard notation. This is going to be summation little L2 norm of the sequence is just, as always, the sum of squares, square root. And it turns out that one has something called Parsifal's theorem. Parsifal's theorem tells you that that the little L2 norm of the sequence is equal to the L2 norm of the function. Okay. So the little L2 norm of the sequence is the same thing as the L2 norm of the function itself. Okay, Parsifal's. Okay, and it's possible to show that other similar things hold. For example, that the L infinity norm, the little L infinity norm of this is bounded above by the L1 norm of the function. Okay, and it's also possible to show that the L infinity norm of the function is bounded above by the little L1 norm, little L1 norm of the sequence. Okay. So the way you want to think about this is that we have these bounds, right? These bounds going from big L2 to little L2, from big L1 to little L infinity, right? From little L2 to big L2, from little L1 to big L infinity, right? And so the question you should have is, what about for arbitrary p, right? For p between 1 and infinity, can we get the intermediate results, right? Is it true that, for example, the little LP norm of the sequence is bounded above by the big LP prime norm of the function, right? Or similarly for the second statement, right? That's for p between 2 and infinity, say, or that's to say for p prime between 1 and 2. Let me write this backwards. Right. So for p between 1 and 2, okay. The statement is true for p equals 1, right? The statement is true for p equals 1, and it's true for p equals 2. Is it true for p between 1 and 2? And so these are, it's this sort of result that we're going to get a tool today that allows you to get the intermediate bounds. Okay, these are so-called interpolation theorems. These are really great. These are great because you just need to prove the endpoint bounds, and then you get out everything in between. Okay, anytime you get a pair of bounds, then you can also get intermediate results. So that's the motivation. Any questions? Any questions? No? Is everyone okay? Okay, good. We're in a very, very silent class. It's the most silent class I teach. Why is that? Why is that? Why is that?
Are we the oldest class?
Yes, you are. Are you saying that as people get older, they become more silent?
Are we louder than your children? Are your children louder than us?
Yes, that's true. But I think I've been about the same level of silence my whole life. One time when I was in junior high school, my orchestra teacher told my mother that I had been laughing in class. That is to say that was the first time she heard me laughing. Since she had helped me, I had her do elementary school as well. So I guess I've only become louder. Okay. Okay. So that's where we're heading. But before we get there, we're going to do a little bit of a digression, which will seem irrelevant now, but will become very relevant shortly. Okay. So slide and apparent digression. Okay. So again, let's go back to the function in L2. We've got some function in L2, but you've got the Fourier series. Got this Fourier series, summation a sub n e to the I theta, right, where a sub n is defined as being, you take the function against e to the I theta, right, you take the inner product of that against e to the I theta on L2, 0 to pi. Okay, we define the conjugate function. Define the conjugate function f tilde by I f tilde theta is the function associated, the function with the Fourier series sine n a sub n e to the I theta. So that is, right, to every function you have an associated Fourier coefficients, right? Right, you've got these Fourier coefficients, a sub 1, a sub 0, a sub negative 1, etc. Right? And what this is saying is that you create a new Fourier series by preserving the guys on the right, multiplying the guys on the left by 0, multiplying the 0th Fourier coefficient by 0. I'm sorry, multiplying these guys on the left by negative 1, multiplying the 0th one by 0. Okay, and you divide that thing by I, and you get a function, and that function is called a conjugate function. Okay, this is the way you want to think about it. It's a function that you get by taking the original function. You take the original function, map it to its Fourier series, keep the Fourier coefficients, the positive Fourier coefficients, and flip the negative Fourier coefficients, get rid of the 0th Fourier coefficient, and that gives you a function which, when divided by I, is this conjugate function. Okay. This operation is actually called something called the Hilbert transform, which is the next the thing we'll do in the next section of this chapter. Okay. Okay. So so notice that. So just a sort of a dumb observation. If we take the function and add on the this constant plus I at theta and pi by 2. Well, what's that? That's going to be something with a Fourier series where there are no negative coefficients, right? Because you've got the negative coefficients plus the positive. This one has sign on coefficients, so they cancel off for the negative guys. So it's only going to have the positive Fourier coefficients. Okay. So what this is associated to is this guy here, n from 0 to infinity, a sub n equal to nothing. Okay. So it's just the non-negative terms. Okay. So there's a connection with complex analysis. So connection with complex analysis. And that is that you can define something called the Cauchy integral. Of f on the interior of the unit disk, and you define it like this: f of z is defined to be the integral from 0 to 2 pi of f theta over e to the I theta minus z, I e to the I theta d theta z. Which turns out to be analytic on the disk. Okay, it turns out to be an analytic function, right? Analytic means that it has a power series representation at every point, or it's differential. So those of you who haven't had complex analysis before, it's okay. Just think of this as differentiable. Complex differentiable. So, okay. It turns out that if we look at f on the boundary, right? On the boundary of the unit disk, we get this. We get exactly this. Okay, we get this function. The function that we got that's associated with we get the Fourier series that's associated with this sum here. Okay. So another way of saying this is that if you start off with if f is a real value function, then one can construct an analytic function f on the unit disk whose boundary values so that the real part of the boundary values is f, and the imaginary part is f total. Okay, so this sort of, right, if you have a real value function, is it possible to create a function that's analytic? Is it possible to create an analytic function, right? Can you define, so you've got some real value function, f, right? And you're wondering, can I find a g? Can I find a g so that this sum is an analytic function? Right? Can I find a g so this function is an analytic function? Right? And this is sort of answering that question. Okay, it says that you can construct a function that's analytic such that on the boundary, the real part is f, and the imaginary part is this f twiddle. Okay, so like this f twiddle, in some sense, is what you add on to is the g that you're looking for.
That would be any function in L2?
Yeah. Yeah. I think so. Okay, so that will become more relevant. I should say I'm not so familiar with this theory from the complex side. I'm more familiar with the theory from the real analysis side. So let me make sure that that's true. What I just said is true. It's true. I'm not sure. I think so, but yeah. Okay. So this will become, like I said, this will become really relevant once we get to the next section and start talking about the Hilbert transform, which basically is, you can think of it as the map from f to f twiddle, from taking the function and mapping it to its conjugate function. Which turns out to be key in the study of the convergence of Fourier series. And sort of the prototypical example of something called a singular integral. Which is like a huge, one of the central topics of analysis. So the Hilbert transform is like the first example of a singular integral. Okay, so enough of the digression. Now we are going to head towards Riesz interpolation. Okay, so and we'll see if we can do it today. I think we should be. Okay, so just some notation. We let L P0 plus LP1 be all functions f, such that f can be written as f0 plus f1, where, of course, f0 is an LP0, f1 is an LP1.
This is the MP now? This space is not the MP now, or like the MP? Oh, no, this is the no.
I'm just saying that
Space.
we're going to call this space the guys who can be expressed. Any function that can be split into two parts. One part is in LP0, the other part is in LP1. Okay. And now we're going to give the statement of the Riesz interpolation theorem. Let's say that T is a linear mapping to LQ naught plus LQ1, where Pi is Q naught prime. So P naught and Q naught are dual, P1 and Q1 are dual. If T is bounded from LP naught to LQ naught with bound M naught, and T is bounded from LP1 to LQ1 with bound M1, T is bounded from LP naught to LQ naught with bound M naught, and from LP1 to LQ1 with bound M1, then T is bounded from LP to LQ for any pair P and Q such that 1 over P equals 1 over T over P naught plus T over Q naught. 1 over Q equals 1 minus T over P1 plus T over Q1. So you draw these straight lines, right? You have these straight lines going from 1 over P naught to 1 over Q naught, right? And from 1 over P1 to 1 over Q1, you say, okay, if we call the corresponding points 1 over P and 1 over Q, then the T is bounded from P to Q, LP to LP. And notice that, right, we said that P naught and Q naught were dual, P1 and Q1 were dual, and so P and Q are dual also. Right? P and Q are dual. Notice that. Notice P and Q are dual. Right? Because if you add this together, you get 1 over T, 1 minus T plus T. Just one. See, so again, you have bounds at some points, and you're wondering about the intermediary bounds. And it turns out that T actually is bounded on those intermediary bounds. Okay. So, for example, what we were just talking about, right? Right, if we call T from L2 0 to pi to L2 z, the map from F to its Fourier coefficients, the map from F to its Fourier coefficients, well, Parsifal's theorem says, as we said before, that TF L2 equals F capital L2, right? And it's obvious that TF L infinity is less than or equal to FL1 because so why is this obvious? Right, this thing is the absolute value of f beta equal to divided beta theta. Right? Well, why is that controlled by the L1 norm? The end. Right, trying to right. This is bounded by this. Okay. And that's the norm that is 1. Right, the norm of any real number to a purely imaginary power is 1. Okay. So that so what does that say? That says that we have these endpoint bounds, right? And so that gives you that TF LP L prime is bounded above by the LP norm for P between 1 and 2. And we had the endpoints already. I forgot to say that the bound, T is bounded with bound n naught, bound smaller than n naught 1 to the 1 minus t times n1 to the c. So here that number is 1.
In the schema theorem,
Yeah.
is LP over the circle, or is it any space?
No, it's any space. It's any box space. Or it'll be any sigma finite vector space. Okay, so you see that Riesz interpolation is a useful thing. At least it seems like it's going to be useful. So let's get it. Okay. Now the proof of this relies on a lemma from complex analysis. I think I'm just going to state the lemma and then we'll use it since some of you haven't seen complex analysis. So I'm just going to state it. So here it is. Let P be a holomorphic function. So holomorphic and analytic are the same terms. Complex differentiable. Regular. And all those terms mean the same thing if you see them. Just a function that's differentiable in the complex sense. So let phi be a holomorphic function on the strip S. So the strip S is the guise for which the real part of Z lies between 0 and 1. So you have a complex plane, and you're looking at here's 1, and here's R, here's IR. So you're looking at this strip here, this is S. Okay. You have some function that's holomorphic on it. Let's say that such that phi is continuous and bounded on S closure. So it's continuous and bounded on the closure of that strip. With bound and not on the left boundary, and one on the right. So the size of phi is controlled on the left bar, on the left on the left line, and is controlled on the right line, okay, by n1. Then, in fact, if we look at if we look at phi for some fixed t, so pick some real number t between 0 and 1, and look at the size of phi on that line. Okay, look at the size of phi on that line. If we take the supremum on that line of the values of the modular of the sizes of phi, it turns out that that thing is bounded by this. So for every line in between, we have these bounds. Okay. And this will be this is going to be the key tool that we'll use to get the Riesz Interpolation Theorem. And so this is called, they call this the three lines theorem. Okay. So I'm going to assume that, and let's go for the interpolation theorem. So we'll first do the case. We'll first show that T f q is bounded by M f p for f simple. Right. We want to show, right, our goal is to show that T is bounded from LP to LQ, from LP to LQ for these P, for these intermediary P and Q. And we're going to do it in the case for f simple first. Okay. And then we'll play a trick to get us to the general case. And that trick will be a useful one. Okay. Okay. So here we go. Okay. So another key lemma will be lemma 4.2 that we had earlier. So let me recall. It will suffice to show that the supremum over all G of LQ prime norm 1, where G is simple, the supremum of the integral of G against TF is bounded by M of LQ. Okay, so by lemma 4.2. Right. You remember what lemma 4.2 told us? Right? It said that if we're trying to get some control on the size of this thing, right? Here's something. We're trying to get some control on the size of it. Well, it suffices to, we're trying to get some control on the LQ norm of this guy, right? Well, if it turns out that when we integrate that thing against guys of LQ prime norm 1, and we get some bound on that, then this thing turns out to be an LQ with that as its LQ norm, right? That was lemma 4.2, and it's very useful. You see, it's a quite useful thing, right? To get to determine the size, to get some control on the LQ bound of something, well, you try to control the integral of that thing against things in LQ prime norm 1. Okay. You integrate them against these guys, you get some bound on it. That bound turns out to be the LQ prime norm of this, right? Right. So if we can get this, what that tells us is that the LQ norm of TF is controlled by this. Okay. Right. So that's what we're going to do. Right. We want to control this sort of thing for where the G's are LQ prime norm 1 and the G's are simple. Okay. Okay. So just remember lemma 4.2. Now the way that the way we get this bound is really amazing. It's really clever, and of course it uses the three lines lemma. And here's how it goes. Okay, so and then the LQ of TF is controlled by M as the LP norm of F. Okay, so we're going to do this in the case P is less than infinity. P is less than infinity. So Q is bigger than 1 since they're dual to each other. Okay. So this is a pretty clever proof. Here it is. Without loss of generality, we assume let P be an LP. Let F be an LP be a simple function, and without loss of generality, we can assume that the LP norm is 1. Okay. And also let G be an LQ prime, simple and normal. Okay. And we're gonna try to get this bound. Okay. So we want to show star. Okay, so here it is. We are going to for Z in S bar, we're going to define some intermediary functions, FC and GZ. Okay. FZ and GZ. Okay, and here's how we'll do it. We create these coefficients. Here are, these exponents. We're going to have these exponents, gamma z, which is defined to be p times 1 over z p naught plus z over q1, and delta z being q1 minus z over q naught plus z over q1. Okay, and then we let f sub z be the modulus of f to the gamma z times f over the modulus of f. We let g sub z be defined the same way. Okay, and then we let we define phi of z as the integral of gz against tfc against tfc. Okay, and so this is the thing to which we're going to apply the three lines lemma. We will apply the lemma to P. Okay, and that will basically do it for us for the case of simple. Okay. So let's make some observations. observation 1, f sub t is f. Right. Right. Is that obvious? Is that right? Yeah, wait a second. Is that right? That doesn't look like right. F sub t, F sub t, right? So it's obvious when I wrote it down yesterday, but F sub t is going to be F to the gamma t F, right? Well, gamma of t, this is going to give us no, it is obvious. It is obvious. Right? Because you get 1 minus t over p naught plus t over p1, right? But 1 over p is actually that, right? That's 1 minus t over p naught plus t over p1 is 1 over p, right? So we get p over p, right? Right? So we get this equals this to the 1, f over that, right? So it's f. So it's obvious. Okay. And similarly, g sub t is g. Okay. Second observation, which I think again is obvious. F sub z's p naught norm is 1 when the real part of z is 0. Okay. F sub z's p naught norm is 1 when the real part is 0, right? Because then what do we have? F sub z is equal to this to the gamma z, and so that's p 1 minus z p naught minus z over p1, right? And then we have this thing, f over f bar, right? And we're looking at the p naught norm, we're looking at this thing, so p naught, right? So there'll be a p naught here, and then there'll be this thing to the p naught, but that's just 1. Right? Okay. So, and then you say, well, look, the real part of z is 0. That means that z is pure imaginary, right? So, so this thing, this exponent here is purely imaginary. It's not going to contribute anything to the norm, right? Whatever it contributes will be a norm 1. Right? Similarly, right, here you're going to be subtracting out the pure imaginary, so this z doesn't contribute anything to the norm either. Right? The only, what you get is that you get f p naught p 1 over p naught. In other words, the modulus of f to the p. Right? And so when you take the p naught norm of fz, when real part of z is 0, you get the LP norm of f. Well, the LP norm of f we assume is 1. Right? Okay. The main thing to remember is what I said earlier, that if you take any real number, right, any real number, and you raise it to an imaginary power, it has modulus 1. Okay. Okay. Observation 3 is the same sort of thing. The P1 norm of FC is 1 when the real part of C is 1. You see what's going to happen, right? Because this thing is P1 minus C over P0 plus C over P1, right? If the real part of C is 1, well then this thing's not going to contribute anything to the norm, right? And you're going to have 1 plus some imaginary number here. So the only thing that's going to contribute is this 1 over P piece of 1, right? So what we're going to get, again, is this thing to the P1 power equals P1, and then the only thing that contributes is this 1 over P piece of 1, right? And so you get the LP norm, right? Same sort of argument. Same reason. Okay. And then similarly, GZ, Q naught prime norm is 1 when the real part is 0, and GZ Q1 prime norm is 1 when the real part is 1. Okay. And these observations allow us to get the bounds on the left and right boundaries of the strip for capital Phi. So you say, well then, thus on the left side of the strip, we have that phi z, which is controlled by the L1 norm of this. Is controlled via Helder's inequality by T FC Q naught GZ Q naught prime. By Helder's inequality, you get that, right? You say, okay, well, GZ, when Z, when on the left-hand side, this is 1, this thing is 1. Right? This thing is 1 by observation 3. And what do we know about this? Well, T is bound, part of our hypothesis was that T was bounded from LP naught to LQ naught. Right? So this is controlled by M naught SC P naught, right, by hypothesis. By hypothesis, right? And remember, M naught was our bound from P naught to Q naught, right? And we also have that that this is 1 by observation 2. So what we have is that on the left side of the strip, we have the bound that phi is controlled by M naught. Okay. You can guess what's going to happen. On the right-hand side of the strip, we're going to get bounded by M1. 3 lines lemma gives us that on any line in the middle, we have the bound, we have that right. So similarly for the right-hand boundary, then the 3 lines lemma the limit says that that this is controlled by lemma to 1 minus t and 1 to the t on wherever the real part, whenever z has real part t, whenever z has real part t. And in particular, thus the integral of tf g, which is b of t, is bounded by m naught 1 minus t and 1 t. And by lemma 4.2, that gives us control on tf's LQ. Isn't it great? Right? Isn't that great? I mean, right, to think, oh, okay, this is what I'm going to do. I'm going to create a holomorphic function that that on the real part gives me the bound. That on the real part agrees with this this integral whose bound I need to control. Okay. And I'll control it. I can control it using this 3 lines lemma. That's pretty. And this is not trivial. This is far from trivial. Okay, and that's so we've done the first part, right? We've done yes, Eric. Yeah.
To use the 3 lines lemma, you need to know beforehand that phi is bounded.
Oh yeah. So sorry, I'm just gonna let you read that part. So you need to show 3 things, right? That phi is holomorphic. That phi is holomorphic on the interior and bounded and continuous on the closure. Okay. And sign gives a small argument to show that I'm missing. Yeah, but you're right. I should say that we need to do that. But let me see if I can quickly, in 5 minutes, show you how to get from the simple case to the general LP case. Okay. Okay. So for general in LP. So, right, we want to show, of course, that TFQ is bounded by some constant. Okay. So, roughly speaking, here's the idea. We take a sequence, right? The simple functions are dense in LP. So take a sequence of simple functions. S of n such that they converge. You have this Cauchy sequence and it converges to F. Okay. So we're given some F and we're going to approximate it using a sequence. So create a sequence that converges to it. Okay, we know that for each of these guys, we have the desired bound. Okay? We just showed that that's true. We already know that this statement is true for these guys. This control, this implies that S of n, I'm sorry, that T of S of n is Cauchy in LP. This, right? because you can, if you look at the difference, right, you want to show that the difference between t of f sub n and t of f sub m is small, right? But you know that that's controlled by the linearity of t. You know that that's controlled by the difference here, and this is a Cauchy sequence, so you can make that small. Right? So, so this implies that that t of f sub n is itself a Cauchy sequence, and so right. So it's a Cauchy sequence in LQ, and what you need, so it suffices to show. So it suffices to show that t of f sub n converges to t sub f pointwise AE. We know that the t of f sub n converge to something. Okay. We know it converges to something. Showing that that these guys converge pointwise AE tells us that that is the something that they converge to. Right? For then TF is the LQ limit of T f sub n. Right? And then the LQ norms of these guys will converge to the LQ norm of T of f. Right? We already know that these guys, LP norms, converge to f, that of f. Right? So you just take limits on both sides, and you get the result. Is that clear? Am I going too fast? I think I'm going too fast. Okay. So what we have to do is show that TF actually is the LQ limit. Right? These guys are a Cauchy sequence in LQ. We'll show that Cauchy sequence actually converges to TF by showing that these guys converge pointwise to it. Okay. I don't have time to do it, but let me just give you the idea, and maybe I'll talk about it next time. The idea is this: you separate. Separate f into f upper and f lower. Okay. F upper and f lower, where f upper is f whenever f is big and it's 0 otherwise, right? And f lower is f whenever f is small and it's 0 otherwise. 0 otherwise. Right? So you separate f into its big parts and its little parts. Okay. And you do that for the f sub n's as well. And then you say, well, this upper guy, Fu will be in LP naught, Fl will be in LP1, assuming that LP naught is smaller than LP1. And then you say, you end up showing that for the S sub n guys, the idea is this: you show that for these guys, well, these guys are in LP naught, and these guys are in LP1 too, right? So you show, we already have the convergence on LP naught, and we, I'll talk about it next time. Yeah, well, see what happens is we'll show that T f sub n u converges to T of f of u, that T f sub n L converges to T f the lower part. And then we can add this together using linearity. Okay, and that this will happen in LP naught, this will happen in LP1, and that will give, happening in any LP gives you the pointwise convergence, pointwise A convergence. and then you add it together. Okay, well, I'll do it quickly at the beginning of next class.